We're going to talk right now about the Reynolds transport theorem. Now, the Reynolds transport theorem allows us to translate between the Lagrangian and Eulerian perspectives. The Lagrangian approach follows a specific amount of mass. Think of it like following a single bird to observe its behavior, or measuring the speed of a single car as it goes from point A to point B. We're following the same substance, the same thing, over a period of time. What's convenient about this is that the physical laws can be applied directly. For instance, Newton's second law, force equals mass times acceleration, is true for a specific amount of mass. The challenge here is that the Lagrangian formulation of our equations, like conservation of mass and linear momentum and so on, are very difficult to apply to a flowing fluid. So we have an Eulerian approach. This observes a particular location in space as the material moves past. Think of it like watching many birds as they fly by, or measuring the speed of many cars as they pass an intersection. That's an example of an Eulerian approach. So these equations can be easier to understand, and they have a lot of practical applications. However, we can't directly use, say, Newton's second law, because we're no longer looking at the same particle of matter. As matter moves through our control volume, you could have changes in the mass and so on that make it difficult to directly apply Newton's second law. So we need to have the ability to convert from the Lagrangian formulation, the control mass formulation, to the control volume formulation before we can really come up with a very useful equation for solving problems. So we do that, in part at least, through the Lagrangian derivative. The Lagrangian derivative is also called the material or substantial derivative, depending on who you're talking to. And it's shown here on the slide. This combines local or Eulerian effects on the right-hand side, where you have the local time derivative at a point and the space derivatives at a time. And you combine those together to get the change experienced by a particular piece of matter, and that's that Lagrangian derivative on the left-hand side of the equation. So we combine those things using the local acceleration, and then the acceleration, the second term there, is the acceleration of the particle as it moves through space. So even if there's no time derivative, if the velocity field is steady, as a particle moves through space, it can still accelerate or decelerate because it's moving along the velocity field. As an example, we can look at acceleration. Acceleration of a fluid particle is the change in its velocity as it moves, or the Lagrangian derivative of velocity. And we can break that down into the local acceleration, or the time derivative of the velocity field, and then what we call the convective or advective acceleration, which is the acceleration of the particle as it moves through space. So even if the velocity field were steady, we would still have a value for the Lagrangian acceleration. It's important to note here that this equation actually represents three equations because the velocity is a vector. So then we have to have a separate equation for the x component, y component, and z component of the velocity vector. This brings us to the Reynolds transport theorem. This is an equation that allows us to convert from a Lagrangian formulation, for instance, in this case, conservation of mass, where d of mass dt is 0 for a control mass. No mass is allowed to cross the boundaries. If we want, we can use Reynolds transport theorem to convert that into an Eulerian form, where 0 equals the right-hand side of the Reynolds transport theorem for mass. Just a note on the signs here, velocity and area are both directional quantities. Area has an outward pointing normal. So we need the sign of the dot product, just like when we talked about flow rates. So if velocity is into CV, the control volume, the dot product is negative. If the velocity is out of the control volume, the dot product is positive. The first term on the left-hand side represents the change of the control mass over an infinitesimal time step, a very, very small delta t, as delta t approaches 0. So that's the change in the control mass. The first term on the right-hand side represents the local time rate of change, right? The local Eulerian derivative of what's going on. And then on that third term is two things. First, the amount of psi that flows out of the control volume with the mass over the infinitesimal time, and the amount of whatever psi is that flows into the control volume to replace whatever mass left. Basically, this equation says however much of psi is stored plus the amount of psi that comes in minus the amount of psi that comes out is the total change. It's important to note that the Reynolds transport theorem is not one of our fundamental balance equations. It's actually a mathematical identity that is used to convert our fundamental balance equations from the Lagrangian form, where they're easy to derive, to the Eulerian form, where they're easier to solve.